Okay, this is lecture 3, the evolution of AI agents. So just this weekend, there's a really nice news flash here. Meta released their Llama 4, and this is actually very interesting because, this is a natively multimodal AI innovation. So Facebook has taken this approach, or Meta has taken this approach to open source or show the world openly what are the weights of these models. They have 3 models here. One is Scout, which has 17 billion active weights or parameters out of a total of 109 billion. But what's really interesting about this model is that it has a context window of over 10 million. So that's a huge window. And I think the trend is going to be to continue to allow people to add more and more into that context window. What it does do, however, is challenge some of the notions of RAG, which is retrieval-augmented generation. So if you can put all your documents and loads and loads of books into the context window, why would you ever need a RAG? There could be arguments made, either way, but it is interesting how Google's Gemini had, I think, a $1 million or $2 million sort of window. Now, Facebook has set the standard to make it even larger, which is 10 million. They also released Maverick, which has 178 billion active parameters out of a 400 billion. This is actually very interesting because they have 128 experts. So these are the smaller models that are more expert. So they're going down the approach of this mixture of expert MOE. And Behemoth at this time was still training, but it's supposed to be released. It's going to have 288 billion active parameters out of a total of 2 trillion parameters, and it has 16 experts. So, we're going bigger, and who knows, in maybe the next 6 months, other companies will release even bigger models. But this is actually very interesting how fast everyone's moving here. Okay, so your assignment number 3 is called Flying Blind because, well, first of all, I want you to read this really nice article entitled How Tech Giants Cut Corners to Harvest Data for AI. And, we'll discuss that a little bit later. But basically, as you'll see in the development of these AI agents, most of the data that has been generated by humanities, not only just the data that's available on the internet and blogs, but also books that were written prior to the internet, all have been incorporated, or much of it has been already incorporated. And, there are some issues about copyright and pending lawsuits, and this is still an open question. So I just want you to read that article because I think it gives you a really interesting summary of, what has happened, and then summarize that in a half a page. And then I want you to watch this vibe coding tutorial and best practices by Matthew Berman. Here I'm with Matthew at the Crew AI event up in New York City at the beginning of April. So this is basically how can you add some global rules that he covers into our Windsurf in order to help develop these applications, or actually sort of do your homework assignment. And we always want to try to use the best practices whenever we do anything in business, especially while we're doing our vibe coding. All right, share the results as usual in the discussion boards, and then also look for other best practices if they're out there, and share that with your classmates. Your vibe coding assignment is called Flying Blind. In the first 2 weeks, you took data from the UC Irvine publicly available website. Those data sets were pretty well known. And this week I'm going to give you a data set that I know you've never seen before. So your assignment here is to add value. And, you have to sort of go in there and try to understand. I'll give you a couple of hints here. So, look at your data, try to build some intuition. Unlike the other 2 assignments, this one actually has multiple files inside the folder that have been zipped up, so you unzip it. try to understand what the format is. You need to first be able to read the data in correctly. And there's two parts to the data. I would say concentrate on those files that have performance in there and try to understand what's going on. So one example is, look at a couple of the files. I think there's too many to look at them all. But the idea is, when does the actual data start? Which row is it? Is it row 4? Is it row 5? Which row is the headings? And under the headings, which columns are important? That's one thing that you need to sort of feed into your prompt as you vibe code this. And then start thinking to yourself, how can an AI analyze this? What is this? What kind of figures can it generate? What would you do with this? So who is this data for? Who can benefit from this data? And try to do your best. I know you're going to get stuck, but in the real world, you're usually given sort of a pretty tough problem to solve. Usually they'll send you into a place where they know there's a lot of data and, nobody's had a lot of success sort of figuring out what's going on with that or how to add value to the organization or business with that data. You'll definitely get stuck, but, you've got all the tools, the AI tools available, ChatGPT, Anthropic's Claude, and whatever you want to use. Okay, so I would suggest understanding and attacking the performance files first. And then if you still have time, try to look and examine and try to add value to the concentration files. Those are much more difficult. And I think you'll get very frustrated if you try to go after the concentration files first. Some things to consider, and this is an acronyms for finance people: SPY, TLT, UUP, PDBC, WBTC. So think performance attribution and so forth. So that's going to give you a little bit of a hint. Remember to make a 3-minute video that you narrate and you discuss what you've done, and also submit this to your discussion in class discussion board. Okay, so here are some best practice tips from Matthew Berman. Part of your assignment is actually watching him sort of walk through. I mean, he's a very senior developer, and he's using vibe coding and Codium in a way that I think is very interesting, and he has a lot of tips for us to learn about. And I think he does a really good job of communicating sort of the advantages and the intuition on how this is working. Some of his global rules is always prefer simple solutions, avoid duplicate code. This one I thought was pretty interesting. Avoid files with over 200 lines of code, refactor at this point. So you want, manageable code. And there's some other ones here, that you can watch and, just take a look at that. And remember, generally in this class and in AI, whenever you can find the best practices, you want to learn them and actually implement them in your class projects or in your assignments. So in order to find these rules on Windsurf, it took a little bit of time here, but there's a Windsurf setting in the bottom corner. And from there, you should get to this page where there's a search bar, and inside you put global rules, and then you can edit these rules and you can add whatever you want to it. And I believe these whatever these global settings are, whenever you are interacting with Windsurf in the prompt, it will add this as well. Okay. Now, today we're going to cover sort of this road to intelligent agents. We're gonna map this out for you guys so you can actually see how it works. And then probably in the next class, we'll start interacting, start building some of these AI agents, and you'll have some intuition on where this stuff is coming from. And remember, we're going to start where the transformers came online, and then we're going to map it all the way to sort of, the current day. And what I'll try to highlight here are those very important developments that kind of shifted this industry on the way it thinks and what it could do. Try to keep the jargon to a minimum, and try to give you a lot of intuition on sort of what's going on here. So this is not a purely academic review. It's kind of a pseudo-academic review. And the goal here is just to give you a little bit of a flavor and what was the story and what were some of those aha moments as we've moved on to AI agent. So first, let's start at the end. What is an agent? So if we're in class, I would ask the students, what's an agent? We go around and everybody would have their own views, and we discuss that. But you could also ask Grok and Claude and ChatGPT, and Claude says that an agent is a software system that perceives its environment, makes decisions, and takes actions to achieve a specific goal. So if we look at ChatGPT 4.5, it says an AI agent is an autonomous computational system designed to perceive its environment, make decisions, and act on those decisions to achieve specific goals, typically with minimal human intervention. So now if you kind of compare these two, there's a lot of things that are similar here. Software systems or computational systems, perceiving its environment or, makes decisions, also acts or takes action to achieve a goal or to achieve a specific goal. So, these are the sort of commonalities. And what we're going to do is we're going to try to understand, when were these things put into play over the course. And we're going to start with the transformers. So, when did it have the ability to perceive and make perceptions? And when did that really come online? When did it get the ability to make decisions and even take actions so that it could sort of achieve this specific goal? So we know from the first class that, the software systems foundational period, this started in the 1940s and 50s and 60s. So one of the important papers is by Alan Turing, Computing, Machinery, and Intelligence. And it sort of establishes theoretical foundations for thinking machines. Everybody was trying to code these machines up and, create programs. So these programs have been around for, from the 1950s. Now, perceiving the environment, this is actually very interesting because what you'll see is that we had a lot of data on the internet. We had all these books that were written before the internet, but we really didn't have a way to take all that information and compress it into sort of a knowledge base, or I'll call like a compressed brain of information. So the transformers in this very famous paper, Attention is All That You Need, allowed for this architectural structure that made large-scale large language models feasible. Also, it actually sort of killed this research strand, recurrent neural networks, LSTM, in gated recurrent units. So GRUs, basically when the transformers came, it used to be the case that people were pursuing this line of research with RNNs, recurrent neural networks, and they were trying to predict the next word using these RNN structures. Unfortunately, what happened was that was very limited, and it took a lot of computational power. And there's also, what we heard of before, the vanishing gradient problem. So when the transformers first came online, people realized that this strand of research, the RNN, the recurrent neural network, wasn't very scalable. And you couldn't sort of, get all that data off the internet and create a real large-scale model because it was computationally very difficult, if not impossible, to bring that much information in. The other thing that was happening a little bit later, and the original transformer paper, I don't think when the authors created it, they knew what was the full impact that we're feeling today, because they use it to transform sort of one language into another language. So it's very limited in terms of its use, although the title was pretty grand. So along the lines, there's also another sort of extension. BERT, which is a bidirectional encoder representation for transformers. And so what BERT did was sort of using this mass language model sort of technique in order to understand tasks. So BERT allowed us to really, understand specific tasks One example is classification. Another example would be a multi-class sort of classification, and another task would be question and answers, and the other one would be a chatbot. So in the early days, we had multiple models depending on the task at hand. So even in Hugging Faces, it would ask, are you trying to do some kind of sentiment analysis, or there would be a different model if you're trying to do some kind of topic modeling or find the topics, and there would be a different model along the same families if it was questions and answers. So, that changed, and then we got into this general, generative sort of more general model that incorporated all these things. But this didn't happen overnight. So, we had GPT-1, we had GPT-2, and it was actually around GPT-3's time when they were adding lots and lots of parameters, and it took, quite a bit of computational power in order to get these models to compress this knowledge, that we started to see some emergent behavior, and we'll talk about that. So GPT-3 was the real one that, they got all the data on the internet and everything else. They sort of, compressed it into these large language models, and this 175 billion parameters kind of had things inside of there that we didn't know, and we were surprised to see, as a community, that it could actually do certain things. And these were basically behavior that nobody expected these models would have been able to do. And that these emergent behaviors only came out after the number of parameters became very large, in the billions. Okay, so, transformers enabled scalable deep learning on text, and BERT demonstrated their power for understanding tasks. GPT-3 was extending this architecture for generative tasks. Remember, before there was very specific things that BERT was trying to do, and it had a pretty good success rate, but it was very specific tasks. So GPT made it a little bit more general, and these three sort of enabled this full LLM to be able to be trained on all of the internet data. I would say the transformers and BERT, in particular, GPT-3 was just a larger model. And we'll see a little bit later that, the more and more parameters it has, as we know from the first class, the more things that these things can do that were in a predictable fashion. So those are the scaling laws. So, people continue to press for bigger models, more data, and so forth. Okay, and now one of the things here to make decisions, so what occurred to allow these large language models to make decisions, at the time there's a lot of research going out. One example here is, few shot learners, and we'll talk about the actual example of how this works. And GPT-3 started to demonstrate some emergent decision-making behavior. So one thing that was really interesting is that you didn't have to change the model, but depending on what you put into the prompt, you could ask it to, tell you how to do something step by step, and putting that into the prompt or giving examples how to solve the problem step by step actually was very helpful. So what's really interesting here is that the model didn't change. You don't have to fine tune the model. You just have to put a smarter prompt in, or you have to put in, sort of examples where you're discussing things sort of step by step. And so this was known as a chain of thought, which, current AI agents use quite often. The other one that was interesting was reason in action. So this sort of intertwined this notion of how do you reason, can you think step by step, and then go out and take an action with tools. And initially the tools were sort of API calls, and you can think of it as, either go into this folder and pull out, these documents, or go on the internet and search. And so this reason in action, or react, was actually very, very interesting. So as people started to understand more and more of what the large language models could do, they wanted to make sure that the more recent information was coming into these models. And remember, in order to train one of these large language models at that particular time, GPT-2, GPT-3, it was on the order of tens of, 30s of millions of dollars. Now it's, hundreds of millions and more. But back then, once you sort of calibrated the model and got the weights, right, set in a nice way, you couldn't roll that to the current information. So the idea was, how do you get more current information into these models that sort of stagnate after they train it, right? So that was this the retrieval augmented generation. It's basically a retrieval system. The intuition there is that you want to put more information into the prompt that is relevant in order to help understand that question. So you take the question, what is the question about? If it's cats or dogs, you go back to your sort of, database of information, and you pull out, if it's cats, then you pull out more information about cats, and you inject it into the prompt. Or if it's dogs, that's a different subject. You go out and you put it into the prompt. And that worked pretty well if you were asking a question about very specific topics, but it didn't work very well if you're trying to combine two topics. So for example, if you wanted to talk about NVIDIA, it would go and pull NVIDIA's information. But if you wanted to talk about Apple, it would go pull Apple's information. But if you wanted to compare the two, it was kind of break down. So it wasn't as good in terms of the first generations of RAG. There's been many generations and updates of RAG. Now they get it to the point where there's these sort of logical trees, and you go down certain branches that make more sense, and you put so that information in. And we'll touch a little bit on that, I think, later on in a couple of classes. Okay, so new prompting strategies like chain of thought, COT, or reason and react enabled structured reasoning, and GPT-3 with 175 billion parameters started to have emergent behavior that was very interesting, because basically we started to notice, wow, this thing that we created actually can do things that were not in the training data, and were not there whenever we pre-trained these models, right? Okay, so it paved the way for retrieval-based methods like RAG, and RAG was addressing a very specific problem at that particular time when it was introduced, to bring real-time information into these large language models, because they were trained, like a month or two before, right? And it was too expensive to sort of train it every day. So here's the actual paper for GPT-3. 175 billion parameters significantly enhanced the few-shot performance across natural language processing tasks, operated effectively in few-shot settings, and we'll cover what that looks like. And also, it excelled at tasks such as questions and answers and sort of reasoning. Some of the challenges faced are still limited in some scenarios, and there was also some hallucinations, right? And remember that a GPT-3 would just try to finish the next word. So if we interacted at that particular time with GPT-3, it wasn't that interesting, because we as human beings like to ask a question, have it respond, like a Q&A, asking questions. We like to chat with it like ChatGPT. So ChatGPT built upon GPT-3, and in a way gave it kind of a better user experience for human beings, right? And we'll talk a little bit about that in a bit. So here's an example of sort of in-context learning. Here's an example of zero shot. So in this example, translate English to French, cheese, and then you sort of put this arrow to what? You don't give it any examples. You don't sort of give it like one shot example. It's a zero shot, just to answer this question. And here's an example of one shot. You actually gave it one example. Sea otter is to Le Tour de Mur. And then cheese is to what, right? So here's a one-shot example, and here's a few-shot examples. Again, you see you putting a couple of more examples in there, and now it's starting to figure out that there's this pattern it has to follow. And these were sort of just adding more to the prompt and sending off to the LLM. So it had some kind of ability to sort of learn in a limited setting this pattern that you're sort of showing it what to do. The chain of thought was actually very interesting, because it's just a prompting technique. You don't change anything in terms of the weights or the LLM. You take it as is, and you ask the LLM, to think about this step by step, or you even put in an example of how you should think about this problem step by step. And then it learns to start thinking step by step. And that was very, very exciting, very interesting. And, that sort of occurred in GPT-3, and that was very surprising to many people. So here's an example. In the standard prompting methodology, here's one question, here's one answer. So you're giving it one example. Roger has 5 tennis balls. He buys 2 more cans of tennis balls. Each can has 3 tennis balls. So how many tennis balls does he have now? So 5 tennis balls plus 2 plus times 3 is 6. 5 plus 6 is 11. Okay, the answer is 11. But you didn't give it, that logic that you use, the chain of thought. Basically, you just said answer is 11. Now, if it's given another question, the cafeteria has 23 apples. If they use 20 to make lunch and bought 6 more, so if they use 20 to make lunch, then it goes from 23 to minus 20, so there's 3. Now you buy 6 more, so 3 plus 6 is 9. How many apples do they have? And it got confused, right? So the answer is 27. Now, here with chain of thought, we don't change anything, but we add more information in the prompt so that it knows that how to think about it, right? So here we have Roger started with 5 balls, 2 cans of 3 balls, each is 6 tennis balls. 5 plus 6 equals 11. So notice that you're explaining inside the prompt how to think about the answer to this problem. Instead of just giving the answer is 11, you guide it, right? But you're just adding this to the prompt. So you're showing it, hey, this is how you should think about it. And then lo and behold, the chain of thought prompting, look what happens. Then the LLM starts to also starts to think this way. The cafeteria, instead of saying the answer is 27, it says, oh, the cafeteria has 23 apples originally. They used 20 to make lunch. So they have 23 minus 20, which is 3. They bought 6 more apples. So they have 3 plus 9 equals 6. Notice it's following, it's mimicking, right, that thought process, but it's obviously doing it for that second question, which was really interesting. So that was a very exciting thing to understand what we were sort of creating. We started sort of created a Frankenstein thing, and then we started poking at it, and we started learning more. And we were very excited that it had much more in there than we thought it initially had. Here's an example of retrieval-augmented generation. The way to think about it, you have a query, but instead of just asking the LLM, your question, what you can do is suppose you have more information, like additional documents, right? That could be proprietary information, or, it could be specific textbooks. Maybe it's on the course of finance, right? So you take that information, text, chapters, sentences, paragraphs, and you put it through an embedding model. So what this does is it takes the words and makes it into this numerical vector, okay? And that is going to be populating you can see number 2, a vector database. And now you index into that vector database, and now that becomes just a numerical vector. So, whenever you ask a question in the prompt, those are sentences and words. Those words can be converted into the vector, and basically you can do now a similarity search of the question that you have, which is a numerical vector. Now you check inside your vector database, what is that question most similar to inside my database? Let's pull out those items, and let's convert those numerical vectors back into text, and you'll see in sort of step 5, now you put these chunks of text back into the question plus your query, and then you send it to the LLM. So what did you do? You just augmented your initial query with some information, text information that you've sort of pulled out from your database, right? And there was, you went from additional documents into this vectorization of this information. You put it in vector database. You took your query. You also made it into a vector. You pulled out, used cosine similarity or whatever you want to do, some kind of measures of how to pull out similar vectors. And then you converted that, whatever you pulled out, into text again. Then you took that text and your query, which was originally in sort of a sentence or words, and you send it through the LLM. And then, people got better responses. So retrieval augmented generation was, pretty popular. There are many companies do this. They provide the services online. Some of them do it inside in the memory of the computer. Some people provide that as service sort of in the cloud. The other one that's interesting is sort of taking action. So now we have the ability to sort of think, we have the ability to reason and also do something and act. And here we're sort of wanting the AI or the agent to start taking life. Some of the things could be going out there and searching for certain things. The other thing, it could be sort of talking to another AI or talking from a LLM to a database. So what's happening now is this Anthropic created this protocol, which is just rules. How these LLM, model context protocol. So similar how an API sort of governs how the front end and the back end will talk, how computers will talk to each other. It's kind of like a waiter who takes the order on the front end, goes to the back end, which is the server, and then brings that information back and forth. So now we have some kind of protocol so that we can have the LLMs start to interact with databases or start to interact with other LLMs and so forth. So this is actually very interesting, and people are getting very excited about MCPs and how this is going to open up, many more opportunities in terms of, allowing these LLMs to, or agents to interact back and forth, interact with data sets, even without the human in there, and then going to get this information, maybe making a report out of it. Maybe another LLM takes a look at the report and generates something from that report and eventually gives it to the human being after a couple of iterations. So this is sort of new territory. People are excited, the technical people are. We haven't seen things that are explosive yet, but I'm sure a lot of startups are incubating things, and I think this is where the MCPs is where, if you solve a really interesting business problem, that you could probably have the one person who's a billionaire putting these agents all together and so forth. So that's my gut says it'll probably happen somewhere in here. Here's an example of reason and react. Aside from the Apple remote, what other device can control the program Apple remote? What other device can control the program Apple remote was originally designed to interact with? And I don't know the answer to this. I'm not that versed in Apple products, but if you just asked it, the standard would be an iPod, and that's not the right answer. If you try to use chain of thought reasoning, so you're adding some more into the prompt, let's think about it step by step. Apple was originally designed to interact with the Apple TV. Apple TV can be controlled by the iPhone, iPad, and iPod. So the answer is iPhone, iPad, and iPod. So chain of thought actually doesn't give you the right answer. That's wrong too. Now, if you just do act only, where you search Apple remote, you get some observations. You search this front row, you get some more observations. You come back and you search front row software, you get some more observations, and that finishes. That also does not give you the correct answer. So in order to do this, you need this reason and action together, which is kind of interesting. So you ask it a question, it'll go out and search, it'll look at the observation, then it'll start thinking about the results, right? Then it'll go out again and it'll search, and then it'll come back with some information and it'll start thinking about it. So this process of thinking first, going out there in the environment, getting more information, coming back, and then rethinking about this or processing or reflecting on this information is the one that can solve this problem, which was really, really interesting. So that's where React comes into play. So, this is a sort of a, very simplified version. You have a particular task, you send it to the LLM. The LLM has the ability to use tools such as, query tools or search tools or so forth. It'll go out and it'll interact with the actual environment. You can think of this as doing some kind of Google search, right? In the current time period, it'll come back with the results, send the results back into the LLM. And this is where it's sort of reflecting on the results or rethinking about, what's going on. It could send it right back out and get more information. And, so this reasoning is actually very interesting So the LLM has the ability to go out, grab more information, pull it back, and then think about it, right? Is this adding more? Do I need to go out and get more information, come back, and then ultimately it comes back to the response. So that's the ReAct framework. So, after those occurrences, we got to sort of these specific goals and, achieving specific goals. Now we have sort of Windsurf. You have a goal in your assignment. You don't really know much about the data. I know you don't, and it doesn't exist out there. So it's, sort of brand new data that you've never seen before. And now you're going to use, some of these tools and the AI agent and, Windsurf in order to help you achieve your goal, which is kind of general. I just said, add value, figure out what's going on and add value. So, you can use that. Crew AI is sort of multi-agents sort of using together. Cursor and Replit are similar to sort of Windsurf. I think Windsurf and Cursor are going to be, the competitors, but it's a big market, it's a growing market, so we'll see what happens. Will it be like Excel and Quattro Pro? I don't know, but those probably whoever can raise the most money will survive, and maybe buy the other one out. Who knows? We'll see how it all plays out. But keep an eye on MCP, and we'll cover that a little bit later, maybe in this class if we have time. So at this point, we would take a break, but I'm just going to sort of power through these slides. So let's talk a little bit about all the data on the internet. And this is actually interesting. So all the data on the internet and things that are the LLMs are pre-trained upon. So we're lucky. We get to just use what these large tech companies have pre-trained their large language models, and then we can use it for specific things. But taking all the data on the internet and books and so forth isn't without its controversies. So here's an example. At this particular time, the Times sues OpenAI and Microsoft over AI use of copyrighted work, right? So copyrighted work, that if you just take somebody's book and just put it into an LLM model, there could be a case made that you just quote, took all their information away. Another argument is that it's just like a human being reading a book, but the counter to that is an AI kind of doesn't forget, like we forget, right? We have so many things that we're reading and doing. Sometimes we'll forget. Recently we're seeing this. OpenAI wants license to steal copyrighted materials in a plea to President Trump. In order for the U.S. to stay ahead in the AI race, they make an argument that says, hey, you got to leave us alone so we can, push this research forward and so forth. So we'll see how it all plays out. But what I want to show you here is that sort of all this data on the internet is sitting in this sort of bucket here on the left. Now, the way this kind of works, at least the way that I sort of think about it, is that all this data on the internet kind of gets compressed. And that compression is, due in part to the transformers architectural structure and sort of the BERT that showed that it can actually, perform really well with tasks. And as we scale these up, at the point where GPT-3 was coming out, we got some of these really interesting emergent sort of abilities. We slapped a front end on to GPT-3, and then we made it very user-friendly for human beings. And then we constantly wanted to make it more exciting for us. So can we put in, can we use it to reason? Can we use it to go out there and get information from the environment? Can it come back? Can it think about these things? And can it go out and do more things? Can it interact with other agents and so forth? And so that's where we're getting a lot of these types of products from, these innovations that occurred here. So, I just mentioned this, but the way that I think about it is you have all the data on the internet, and transformers and BERT allows us to compress it or zip it all up. And, this is kind of a zipped up, compressed version of all that information on the internet, including all the, thought processes and reasonings and steps and so forth, expertise. And, as we are historically we interacted with it, we found some really cool emergent abilities in there, chain of thought, one of them. And, it'll surprise us again. So in order to get this into a usable fashion, ChatGPT and, OpenAI did this great thing where they got this reinforcement learning with human feedback. So basically, they asked it questions, and they gave it some answers, and the humans kind of ordered the answers. And now we're basically putting a really nice user interface on top of ChatGPT 3.5. But the core engine, was GPT-3 3.5, which was sort of built on the transformer architectural structure. And so ChatGPT launched in 2022, and this is where it became very mainstream because everyone can interact with a chatbot. You don't need any technical skills there. And so, as people became more and more familiar with how to interact with a chatbot, we started to, developers and researchers started to put more tools in the hands of people. And hence, we're at Windsurf, where you guys, most of you who never coded before or coded very little, can now sort of create these, applications and do things that you probably would have taken you a lot longer before. Once we got ChatGPT, it became mainstream, and then we got a couple of more things added to this. But I think like a lot of these things, whether it's retrieval-augmented generation, is basically adding more information to the prompt. I think the chain of thought, or think about this, or lay out steps that you should do, and then do these steps. That's very interesting. And we shouldn't be surprised because, this is trained on all the things that, we've written as human beings. And typically, if you're giving some complex tests to a human being or a student or even a professor, they'll lay down a game plan of what they'll do first and what they'll do the second and third and fourth and so forth. And then they'll go in there and start, marking off what they need to do. And that's not only for us, students, teachers, for businesses and so forth, right? So that shouldn't surprise us that much if we think about it, sort of how we behave, right? So the essence of humanity is in there, and we're sort of pulling that out and, allowing everyone to use it. Okay, there's a few more topics here that I just want to cover a little bit. One of them is talking about, RNNs and LSTMs and GRUs, and then sort of the death of those. Not really a death. They're still around, but they're not as popular as they used to be after the transformers came on the scene. The transformers, as we know, are the foundation sort of for AI agents. And I'll do a small little deep dive into sentences and embeddings. So before transformers, we had recurrent neural networks, and this is an example of it. Basically, the type of neural network designed for processing sequential data. And remember, sentences are words after words, so it's very good for time series, natural language, and speech. However, what happens is that, the idea is that you hold the information inside the hidden state, and you bring that hidden state to the next cell. So at the bottom, you see X, that's the data that goes in. Hyperbolic tangent, you should recognize that. And then when you get out of it, it's a hidden state. Now that hidden state is information that's captured in that cell. So all these cells are linked together, therefore they're reoccurring, and the hidden state gets updated, more data comes in and so forth. But given the structure of how recurrent neural networks works, they're very susceptible to the vanishing gradient problem. And it was harder and more computationally expensive in order to train these, right? For me, and it depends on who you are, some people like to look at these figures. This is RNN, LSTM, and GRUs, the gated recurrent units. For me, some people like to look at these figures and how the information flows in at the bottom. That's always the data, and goes inside. For the long short-term memory, there's a forget gate, and there's an output gate, input gate, output gate. For the GRUs, it's sort of similar in the structure. But for me, I kind of like to look at the math. And, I look at W's and U's, and I know those are the parameters that have to be updated. I look at X's, I know that's the data that's entering into that cell. And H's is, whenever it's H minus 1, that was the previous hidden layers information coming back into. So that's how the recurrent sort of happens. There's a couple of sigmoids in here, and hyperbolic tangents, and there's some kind of sort of weighting that happens here. But, once you have the data and now you have to figure out what the parameters are, it goes through sort of the same rigmarole, meaning that you have to have some kind of objective function, and you want to try to minimize loss on that function, and you do it through gradient descent. And, while the math may be complicated, the idea is pretty simple. And, each of these has its own benefits. But remember, once 2019, we actually did something for HHS, the CIO of HHS. We did one of these pilots, and we were using at that time an LSTM. So, here's the press release. The CIO of HHS, one of the top priorities, engaging with industry partners and testing advanced technologies. So in 2019, LSTM was the cutting edge. The third test pilot is a long short-term memory recurrent neural network employing a set of algorithms and predictive modeling. This type of network can analyze statement of works and compare them with personal data to determine whether the work is inherently governmental or not. So notice it's a classification task. Given this information, is it inherently governmental or is it not inherently governmental? And so we did that, but quickly. LSTM came on the scene, so people stopped using, or they just sort of, they lost interest in using LSTMs and started using the transformer technology. And we were similar, so we moved on from LSTMs to using GPT-2, fine-tuning that, and solving some problems, or at least trying to come up with some solutions for the VA. And so that's that. Lastly, let's just do a real quick, deeper dive into sentences and embeddings so you can build some intuition on what's going on here. Here's a quote by Patton. Success is how high you bounce when you hit bottom. So, hopefully in your career, it'll always be on an upward trajectory, but the financial markets are up and down. Sometimes you're going to hit bottom. So success is how high you bounce when you hit this bottom. Everyone knows Professor Liew has hit the bottom a couple of times, but just don't give up, right? All right, so we started sentences. We're going to talk about token IDs, and then we're going to go to embeddings. So in this sentence here, success is how high you bounce when you hit bottom. Notice that you can break that out, sentences and tokens. You can think of tokens almost like a word, but the reality is that for 100 tokens, you have about 75 words. So that's basically how it works. Now, these tokens have a token ID. So here's an example of the token ID. So, success is how, notice that it's actually a number. But the token IDs are not embeddings, and that's very important. The token IDs are actually the index for the embeddings. Embeddings are numerical representations of these tokens. So here's an example. You can think of it as an array of numerical numbers, or a vector, or some people call them tensors. But basically, it's just a vector of numbers. And that vector of numbers has certain characteristics. So, for example, if you plotted out, a high-dimensional vector, but you can always compress that information into 3 dimensions. So these, embeddings, word embeddings, are numerical vectors. So similar words are sort of in the similar space. So, for example, on the country and capital, you can see, Russia and Moscow, Japan and Tokyo, Vietnam and Hanoi. They're sort of close to each other. So that's the country, and that's the capital of the country. Verb tenses are close together. So walking and walked will be close together. Swimming and swam will be close together. Now, the one that was really interesting and kind of shocking was this technique in order to get to numerical vectors called word to vec. And here, what they did was they noticed that if you take the vector of king and you subtract off man, the vector of man that points to man, and you take that difference between king and man, that's a vector, you can add it to woman, and once you add that difference to the vector woman, you get to this vector queen. So some of these really interesting relationships sort of held up. All the rules in matrix algebra hold, whether you're in 1 dimension, 2 dimensions, 784 dimensions, or thousands of dimensions, right? So I think in order to really sort of appreciate and understand what AI is doing, understanding matrix multiplication, how to multiply a matrix and a vector, and all the tricks that you can do with the matrices in terms of decomposing it into sort of orthogonal things, right? That like principal component analysis, factor analysis, those all sort of come into play at a certain point if you really want to understand this industry. Okay. And here's an example where we're showing like what are we paying attention to. So if you look at the words, success is how high you bounce when you hit bottom. Now, when you are at you, what is it sort of thinking about? So in the middle one, you see that you and hit are important together, and then what we notice here is how sensitive or what is the model paying attention to. And so, there's different layers, and you can see across the different layers, it's very complex. So whenever you are trying to predict the word you, or when she predicted the word you, what is it relying on? Well, it depends on which layer you're in, right? Certain layers, it's pointing back to the first you, right? Other layers, it's sort of emphasizing you hit. And then another layer would be when you. So there's a lot of complex things going on inside this attention layer of the transformer. And people have tried to use visualizations in order to see what's happening. The other thing that people find out is like long-term dependency. So if I started a story as Catherine went to the market, bought a couple of apples and oranges, then she went outside to eat them, it would know that she was Catherine and them was, the fruits maybe that she bought, right? So that long-term dependencies, transformers do a really good job of that. And I think, that's one of the ways they really shine. And also being able to capture these, sort of complex relationship between different words or tokens in many different dimensions is, pulling out a lot of the complexities there. Okay, so that is that. I'm going to stop this now. All right.